Sathyabama Institute of Science and Technology.
Dear learners, welcome you all. I am Dr. Sathish, Associate Professor, Department of Chemical Engineering, Sathyabama Institute of Science and Technology. Welcome you all for Module 1, Fundamentals of Stoichiometry. In this lecture, we are going to discuss about the mole concept. As mole is the unit of measurement about the amount of substance. The mole is the specific measurements which related to the number of atoms of 12 grams of carbon atoms. And another parameter is the molecular weight, is the sum of atomic weight of the elements constituting in a molecule. For example, if we are having H2O, the hydrogen constitute 1 and oxygen 16. So 2 hydrogen atoms, we will have 2 plus 16, 18. So the molecular weight of water molecule is 18. Then mass, as we know that mass is the property that reflects the quantity of the matter within the samples. So when we have moles is equal to mass by molecular weight. And if we are having a number of gram atoms of the element is equal to number of gram atoms of the element divided by the atomic weight. And number of gram molecules of that compound if you are taking, then it is number of grams of the compound divided by the molecular weight of that compound. When we are discussing about the flow rates, we will have three different types of flow rates. One is mass flow rate, second one is molar flow rate, and third one is volumetric flow rate. The mass flow rate is the amount of mass of the material that passes through the reference point. Then when we say molar flow rate is the number of moles of the material passes unit time. When we are having volumetric flow rate, the volume of the material that passes through from the reference point in the unit time. So M mass flow rate is equal to mass per unit time, number of molar flow rate moles per unit time, and when we say volumetric flow rate, it's volume per unit time. So what's a concept called mole fraction? So when we are having several ways of expressing the concentration, one of that way is mole fraction. So what is the mole fraction? If we are saying for that particular compound, it's number of moles of solute divided by the total number of moles. So for example, when we take the problem number 1, calculate the mole fraction of NaCl and water if 0.01 moles of NaCl is dissolved in 100 grams of water. So we recall the formulas, that is moles is equal to weight by molecular weight, and mole fraction is nothing but moles of solute divided by total number of moles. So here the moles of NaCl is 0.01, it's given. For water it is given in the mass unit basis. So 100 grams we have to divide it by molecular weight. So the moles of water is 100 gram divided by 18 gram per gram mole. We will get 5.5 gram moles of water. So the total number of moles is 0.01 moles of NaCl plus 5.5 gram moles of water. The total is 5.56 moles. So what is mole fraction? Mole fraction is nothing but moles of the solute divided by total number of moles. That is 0.01 divided by 5.56, that is equal to 0.018. So the mole fraction of NaCl and mole fraction of water is 5.55 gram moles of water divided by 5.56 gram moles of total moles, that is equal to 0.99. When we check it out, the moles of water and moles of NaCl, mole fraction of NaCl and mole fraction of water, it is 0.018 and 0.99. That means the sum of mole fraction is equal to 1. So when we say the material balance, so we will have a common material balance called input plus generation minus output is equal to accumulation plus consumption. So when we bring the consumption to this side, input plus generation minus output minus consumption is equal to accumulation. So what is term about input? Input, what are all the materials fed into the reactor? Output, what are all the materials leave the reactor? Examples, products, byproducts and unreacted substances. The production, how much amount of the products will be formed, and accumulation, the material which is within the system, and consumptions, how much material is consumed and it will be converted into the products. So that is input plus makeup materials plus recycles as fed into the reactor. The output may be the products, byproducts and the unreacted reactants. So we will see the mass and mole concepts. Now we are converting the mole basis to mass basis and mass basis to mole basis. So take an example, this question number 2. Air contains 21% of oxygen and 79% of nitrogen by mole basis. We have to convert this problem, express the air composition in mass percentage. Recall the formulas. Moles is equal to weight by molecular weight. So we will have two components. One component is oxygen and another component is nitrogen. The percentage they are given is 79 and 21. So correspondingly we mention the mole percentage. Oxygen is 21%, nitrogen is 79%. The total is 100%. We will take a basis of 100 moles. Then oxygen is 21% of 100 moles is 21 moles. Nitrogen is 79% of 100 moles is 79. So the total, if you check it out, it is 100 moles. It will matches with the basis. Then the molecular weight of oxygen O2 is 32. Molecular weight of nitrogen N2 is 14 plus 14, 28. So we know that moles is equal to weight by molecular weight. So weight is equal to moles into molecular weight. That is 21 into 32 is the weight of oxygen. 79 into 28 is the weight of nitrogen. So the total weight is 2884. Convert the weight into weight fraction. As we know that weight fraction, weight divided by total weight. That is 672 divided by 2884, that will give 0.233. Similarly, 2212 divided by 2884 gives 0.766. The sum of fraction is equal to 1. So the weight fraction of oxygen 0.233 and weight fraction of nitrogen is 0.766. Sum it up, we will get it in 1. If we want to express in the form of weight percentage, multiply by 100, so 0.233 into 100, 23.3, and 0.766 into 100, 76.6. So the total weight percentage is 100. This is how we have to convert the mole basis into weight basis. When we look into the problem number 3, they are given one compound, a compound whose molecular weight is 106. And the composition on weight basis, they are given carbon is 85%, hydrogen is 5%, nitrogen is 10%. We have to find the molecular formula of that compound. So we take a basis. We know that the molecular weight is 106. The unit of molecular weight is gram per gram mole or kilogram per kilomole. That means 106 kg per kilomole of that compound. All things we have to convert into mole basis and atom basis. Then carbon atom, if you check it out, it is 85%. So 85% of 106. 106 is the total molecular weight of that compound. So 85% of 106 is nothing but 90.1 kg. So if we want to calculate how much atoms of carbon is present, 90.1 divided by the 12, that is the atomic weight of carbon, that will give you 7.5, round it up to 8. Similarly, hydrogen is 5%. 5% of this 106, that is nothing but 5.3 kg. Again, you have to divide it by the atomic weight of the hydrogen. So 5.3 divided by 1, that is 5.3. Round it up, you will get 5. Nitrogen, similarly, nitrogen is 10% of 106. So 10 by 100 into 106, that is 10.6 kg. Divide by atomic weight nitrogen 14. So 10.6 by 14 will give you 0.76. On round it up, it will be 1. So carbon 8 atoms, hydrogen 5 atoms, and nitrogen 1 atoms. So the molecular formula, that compound formula is C8H5 and N. So this is a problems for practice. You have the formulas. Gram atom of an element is equal to weight in grams divided by atomic weight. Moles is equal to mass by molecular weight, and average molecular weight is total number of mass divided by total number of moles. So these problems you practiced based on the formulas which we discussed earlier. So from this lecture, we know what is the moles, how we have to convert moles to mass and mass to moles. We have an examples and how to calculate the molecular formula of the particular compound. So for any queries, please contact sathish.chemical@sathyabama.ac.in. Thank you all.